Welcome to this comprehensive guide on C# object pooling, a powerful technique for optimizing performance in your applications. It's fundamental for developing high-performance software systems efficiently. Object pooling is a software design pattern enhancing performance by reusing objects instead of constantly creating and destroying them. This minimizes resource consumption and improves overall efficiency. This approach drastically reduces overhead from object instantiation and garbage collection. These are common performance bottlenecks that severely impact application responsiveness, stability, and user experience. It's particularly useful for expensive operations like establishing database connections, managing network sockets, or handling large data structures. These tasks are costly to repeat frequently. Today, we'll explore why object pooling is crucial, especially in high-throughput systems like games or real-time applications. It ensures consistent performance under heavy load conditions. First, let's understand the problem: the performance cost of frequently creating and destroying objects. This continuous cycle drains system resources and valuable CPU time unnecessarily. Consider a common C# loop where we repeatedly instantiate new objects using the new keyword. This operation accumulates significant performance penalties over time in critical application paths. Each time new is invoked, the system allocates memory for the new object. This involves finding a suitable block, reserving it, and initializing the object, consuming valuable CPU cycles. When objects are no longer referenced, they become candidates for garbage collection. Memory isn't immediately reclaimed by the .NET runtime, leading to temporary bloat and inefficiency. Garbage collection reclaims memory from unused objects. While essential, the GC process introduces a performance cost, often causing temporary pauses or stutters in execution. Frequent object creation and destruction lead to significant overhead, causing application slowdowns or stutters. This directly impacts software fluidity and responsiveness, degrading user experience. This overhead is particularly noticeable in scenarios demanding high frame rates or rapid response times, such as game development or real-time simulations. Micropauses have significant consequences. Now, let's introduce the solution: object pooling. This elegant design pattern offers a strategic alternative to traditional object lifecycle management, focusing on efficient reuse. The core idea is to maintain a pool of ready-to-use objects instead of creating new ones on demand. Objects are kept alive and available, minimizing allocation pressure. When an object is needed, we retrieve it from the pool. When no longer needed, we return it for future reuse, avoiding new allocations and reducing GC load. This significantly reduces memory allocation and garbage collection cycles. It leads to smoother, more consistent performance, fewer application pauses, and a responsive user experience. Let's look at how to implement a basic object pool class in C#. We'll provide a concrete foundation for its application, demonstrating the core components involved. The pool will typically use a collection, like a queue or stack, to store available objects. These choices depend on specific requirements and usage patterns. The core logic involves two main methods: getObject for providing an object to the caller, and returnObject for placing it back into the pool. The getObject method retrieves an object from the pool. Its primary function is to efficiently provide an available object, avoiding the costly process of new instantiation. If the pool is empty, getObject creates a new object to fulfill the request. This ensures the application always receives an object, even if the pool is initially undersized. The returnObject method places an object back into the pool when no longer needed. It makes it available for subsequent reuse, optimizing resource use greatly. Now, let's walk through a step-by-step implementation. We will construct a functional object pool, demonstrating each component and its role in the overall design. First, we'll create a simple GameObject class that will be pooled. This class serves as the concrete type of object we intend to manage efficiently. This class represents any type of object you wish to manage efficiently through pooling. In a real-world scenario, this could be bullets, database connections, or network packets. Next, we'll build our object pool class, which handles the storage and retrieval logic. It encapsulates all necessary logic for object lifecycle management efficiently. The object pool will be generic, allowing it to manage any type of object. This promotes code reusability without rewriting pooling logic for each distinct class. We'll implement the getObject method, checking if the pool has available objects. It prioritizes reuse over new allocation, ensuring efficiency and reducing memory pressure. If the pool is empty, a new object is created using a factory function or a simple new call. This ensures an object is always provided, maintaining application flow. Then, we'll implement returnObject, adding the object back to our internal collection. It's crucial to ensure the object is in a suitable state for reuse. Crucially, before returning an object, we must reset its state to a default or initial condition. This prevents unexpected behavior or bugs from previous usage. Finally, we'll refactor our initial bad code, which frequently created new objects, to now use our object pool. This showcases a direct application for performance improvement. This transformation will demonstrate the practical application of object pooling. It illustrates the shift from inefficient instantiation to a more optimized, reuse-based approach. Now, let's compare the performance before and after implementing object pooling. We'll examine metrics and behavior to quantify the benefits and empirical evidence. Without pooling, we see frequent spikes in memory usage and garbage collection activity. These correlate with constant object allocation, consuming CPU cycles and causing pauses. These spikes translate to noticeable hitches or slowdowns in the application. This degradation impacts user experience, leading to a perception of poor performance. With object pooling, the memory footprint becomes much more stable and predictable. Reusing objects drastically reduces new memory allocations, leading to a flatter profile. Garbage collection events are significantly reduced, leading to improved frame rates and faster response times. This creates a much smoother and more consistent user experience. This conceptual before and after comparison highlights the dramatic efficiency gains. It underscores how a strategic design pattern transforms resource utilization and responsiveness. Let's cover some helpful tips and best practices for using object pooling effectively. These guidelines maximize benefits while minimizing complexities for robust implementations. Object pooling is ideal when object creation is costly or when a limited number of resources need efficient sharing. This prevents resource exhaustion in demanding scenarios. However, avoid it for simple, lightweight objects where the pooling overhead might exceed the benefits. This adds unnecessary complexity and can be counterproductive. Always remember the importance of resetting an object state when it's returned to the pool. This is vital for data integrity and preventing unexpected behavior or bugs. Failing to reset state can lead to subtle and hard-to-debug issues. Dirty objects, when reused, cause unpredictable behavior and logical errors that manifest intermittently. For multi-threaded applications, thread safety is a critical consideration. Concurrent access can lead to race conditions, data corruption, or unexpected behavior if not managed. Use concurrent collections like concurrent-bag or implement explicit locking mechanisms to ensure safe access to the pool. This prevents race conditions and ensures data integrity. While object pooling helps minimize garbage collection pauses, it's not a silver bullet for all performance problems. It's one powerful tool in a comprehensive optimization strategy. Use it judiciously where its benefits truly outweigh the implementation complexity. Always profile your application to identify specific hotspots for optimal impact. In summary, object pooling is a powerful pattern for reducing overhead and improving performance in C# applications. It's a cornerstone technique for building responsive software. By reusing objects, you can achieve smoother execution, especially in resource-intensive scenarios. This leads to consistent performance in demanding applications effectively. We've covered the problem of frequent object creation, the solution of object pooling, and its practical implementation. We explored the why behind the problem and the how. Remember to reset object states and consider thread safety for robust implementations. This prevents subtle issues and ensures application stability, especially in concurrent environments. We encourage you to apply this pattern in your own C# projects to build more efficient and responsive applications. This leads to a better user experience and optimized resource management. Thank you for watching this comprehensive guide on C# object pooling. We hope you found it informative and empowering for your development journey. Happy coding!